In this module, we will again talk about the temperature control system. So, as concerned the temperature control in fermenters, in this slide you can see that the laboratory scale fermenters and pilot and the large scale industrial scale fermenters, as concerned the heating requirement in laboratory scale fermenters, mostly the electric heaters are used. But in case of the pilot and industrial scale, steam generated in boilers is mostly used. So as concerned the cooling requirement, that is met through the tap water in lab scale or with the refrigerated water. But in case of the large scale fermentations, cooling water produced by cooling tower of the refrigerants such as ammonia, etc. So that's mostly the mechanism or the strategy to control the temperature of the jacket and the cooling coil. As we have seen that how we have to control the temperature, as I have already told you that unless and otherwise, if we know about that what are the factors which affect the change in the temperature of the fermentation system. So in this slide, we can easily understand that what are the different factors, or we can say that contributing factors of, or disturbing factors of the temperature in a fermentation vessel. So here you can see the equation Q met plus Q Ag plus Q gas is equal to Q accumulation plus Q exchange plus Q evaporation plus Q sensitive. So here you can see that Q met, that is the heat generation rate due to the microbial metabolism. So we know that when there is a metabolic process, then the heat is generated. So the heat generated through metabolic pathway of the cells. And then when there is a agitation, then there is a resistance. So in a result of the agitation, then the heat is produced. So that is denoted by the QAG, Ag from agitation. And then is the Q gas. So the Q gas is the heat generation rate due to the aeration power input, because when the aeration is sparged into the fermentation media, then have a resistance, and that's why due to that then there is a heat production. So as concerned, these are the three factors which can add the heat into the system. But on the other hand, Q accumulation, that heat is somehow accumulated by the system. And Q exchange, that is the net change, is the actual difference of the addition and the subtraction of that heat of the system. So then is a Q evaporation, mean when there is evaporation, then in the result of the evaporation, heat loss occur. And then is Q SEN, that is meant by the rate of sensible enthalpy gained by the flow stream. So when there is a flow, that's having some absorb of the heat energy. So according to this equation, if we know all these factors, then we can estimate the actually heat required to be exchanged. So just by rearranging the previous equation, you can see here that if we want to calculate, so these three factors which accumulate the heat, which add the heat into the system, and these three factors which contribute to the heat exhaust from the system. So the net change between these two group of factors, then that is the amount of the heat that we require to exchange. But when we know that how much heat is required, so by using this equation, Q exchange is equal to U dot A N dot delta T. Here the A is the heat transfer surface available, that how much is the total area that required for the transfer of the heat, as we have already discussed about in a jacket condition, that the less space is available, but in a cooling coils, then more surface area is available. So Q is the heat transferred, and U is the overall heat transfer coefficient, and delta T is the difference of the temperature. That's mean in later slide I will tell you about that how we can have the change in temperature. If suppose we sterilize the system, at that sterilization system, that is 121 degrees Celsius, and then we have to reduce the temperature up to the 30 degrees Celsius. So the delta T is the difference between 121 degrees Celsius to 30 degrees Celsius. So as concerned the previous equations, it is very difficult and complex to determine all the factors, especially as we have seen in our previous that it is very difficult for us to note the overall heat transfer coefficient, because as concerned the heat transfer coefficient, that vary with the fermentation process. So when the fermentation process will go on, increase of the cells happen. So when there is an increase of the cells and then there is a depletion of the nutrients, that can change the overall heat transfer coefficient. So that's why it is very difficult to calculate the U. So it's why it is sometimes we have to add the surface of the fermenter, since the temperature of the cooling water, the sterilization process, the cultivation temperature, the type of the microorganisms, energy supplied by the stirring. So these are the different factors which can change time to time. So that's why it is very difficult to determine by using this equation. So just an example, if we see that by this example, if suppose there is a cooling area from 50 to 70 meters square having a fermenter of 55,000 liter. So if we want to supply the temperature water at 40 degrees C, so that's we have to reduce the temperature from 120 to 30 degrees Celsius. Then the cooling water require 500 to 200 liters. That's the time is required 2.5 to 4 hours. So this is the equation. As much as the heat, the temperature range minimize or maximize, then we have a different requirement. So that actually when we control the temperature, that can ultimately affect on the cost of the fermentation process.